Hello and welcome to another session in physics. In this session, we'll be looking at the topic reflection of light on curved mirror, and we'll look at types of images produced, their uses, and mirror formula. But before that, let us review the previous lesson. Welcome back. Now let's look at types of curved mirrors. Remember, in our last class we talked about plane mirrors and we also talked about inclined mirrors too. But today we want to look at mirrors that are curved, which are quite different from plane mirrors and inclined mirrors. Now, when a shell of a hollow sphere of glass is made out of a piece of glass and then it is silvered. In other words, put simply, when a glass is made out of a shell or a hollow sphere of glass, a curved or spherical mirror is obtained when it is silvered or coated at the back. Now, these mirrors, due to what we call their curvature, they form images that are quite different from plane mirrors. When we talk about curvature, we're simply referring to how these mirrors are curved. Alright, so if the glass is silvered from outside so that light can be reflected from the inside, we call it a concave or converging mirror. The word converge means to meet at a point. So think of two straight lines or more lines meeting at the point. They are converging. You also come to terms with things like diverge as well. Converge and diverge. So think of converge as meeting at the point, and diverge, this is meeting at the point. Diverge is spreading out from a point. That is diverge. Alright, so if a glass is silvered from outside so that light can be reflected from the inside, it is called concave or converging mirror. So if you don't want to call it concave mirror, you can call it converging mirror. This is what it looks like. Now let's look at convex mirror. Convex mirror is the opposite of concave mirror. Remember, we said concave is also called converging mirror, but this is convex. If coating is done so that the reflection is from the outside, no longer from the inside again, if it is done so that it will be from the outside, it is called convex or diverging mirror. Convex or diverging mirror. Let's look at essential parts of a curved mirror. Essential parts of a curved mirror. The essential parts of a spherical mirror are what we call the aperture, the plough, the center of curvature, and the radius of curvature. The aperture simply refers to the width of the mirror. The pole is the center of the reflecting surface of the curved mirror. The center of curvature, on the other hand, is the center of the sphere of which the mirror forms a part. So these are essential parts of a curved mirror. Already I've mentioned the pole. We also mentioned the center of curvature, C. We've also mentioned the aperture itself, the aperture. So at your own time, you can go back to these diagrams and look at all these things one after the other. Now, what do we mean when we talk about the radius of curvature? The radius of curvature simply is the distance from the pole to the center of curvature. Distance from the pole to the center of curvature. It is the radius of curvature that determines the action of a curved mirror. The radius of curvature determines how a curved mirror will act. On the other hand, for a concave mirror, the radius of curvature is in front, while for a convex mirror, it is behind. The principal axis of a mirror is the parallel line from the pole to the center of curvature. Also, when a beam of light is incident on a curved mirror, the rays are reflected or they are diverged from a point. That point is called a focus. Alternatively also, the principal focus of a concave mirror simply is the point where rays that are parallel and close to the principal axis converge or meet together after reflection. And the principal focus of a convex mirror is the point from which rays that are parallel and close to the principal axis appear to diverge after reflection. So hence, we say that the focus of a concave mirror is real because the converging rays can be seen on the screen, but for a convex mirror, the focus is virtual. It is more like an apparition because it is not so visible. Also, the focal length, which is f for a spherical mirror, is half of its radius of curvature, which means the focal length is f equal to the radius of curvature divided by 2. But if we want to make r the subject of the formula, r becomes equal to 2f, where r is radius of curvature and f is the focal length. So if you're asked to calculate the radius of curvature, you just multiply the focal length by 2. And if you're asked to find the focal length, you divide the radius of curvature by 2 as well. Now let's look at formation of images by spherical mirrors. It's important to note that the position and nature of images that are formed by curved mirrors can be investigated or found out by placing a brightly lit object and a screen in front of the mirror so that the light from the object is incident on the midpoint of the mirror. When you look at this diagram very well, you look at it critically and you see the position of the object and the position at which the image is formed, that they are not just the same. And the position where the image is formed is dependent on where the particular object is placed. Is it AB? Is it at point C? Is it at F in front of the mirror, behind the mirror, and so on and so forth. All these things, these factors put together, will constitute the rules for constructing images that will be formed by a spherical mirror. Sometimes we draw ray diagrams or we construct ray diagrams to help us have a mental depiction or a diagrammatical representation of images that have been formed by a spherical mirror. But we have to follow the following rules when we want to draw ray diagrams. Rule number 1 is that rays parallel to the principal axis will always pass through the principal focus after reflection. The second rule is that rays that pass through the principal focus are reflected parallel to the principal axis. And then the third rule is that rays passing through the center of curvature are reflected back along their path. This is in line with the principle we call the principle of reversibility of light. So what it simply means is that we can always interchange an image and an object at a point or any point in time. I want to make clear the difference between an object and the image. Now, the object is that which is being reflected. In other words, when you stand in front of a mirror, you are the object. Now, that reflection of yours that is formed inside the mirror is your image. Okay? You are not the image, you are the object. Now, yourself that you are seeing inside the mirror, that is the image. So, when it comes to construction of ray diagrams and the rays pass through the center of curvature and then they are reflected back along their path using the principle of reversibility of light, in such a situation, it is possible for both the object and the image to be interchanged with each other. They can be interchanged with each other. Alright, so additionally, the two positions of both the object and the image are called conjugate foci. The reason for this is because the object is placed at any of these positions, and when it is placed at any of these positions, it will also produce an image that is correspondent to the other. Yes, they will produce an image corresponding to one another. So in this particular principle, we can say the image is directly proportional. We can use the sign of proportionality to the object because at any point in time they can be interchanged with each other. So these diagrams are ray diagrams that show the respective positions of the image and the object and how they are proportional to each other and how they can be placed interchangeably. So take time at the end of this video to make reference back to it and sharpen your skills. So let's look at some positions where an object will be placed, and then we'll see the following consequences. Now, when an object is placed at infinity, the image that is formed will be at F. That is for the first instance here, for this A diagram. When an object is placed at infinity, the image will be at point F. This is point F, and this is at infinity. Now, the image formed will also be real, and it will be inverted, and it will also be smaller than the object. Definitely, the image will be smaller than the object. Now, in image B, when an object is placed between F and P, here and here, the image will be formed behind the mirror, and the image will be virtual, erect, and this time it will be larger than the object. Now, what if the object is placed beyond point C? Beyond point C, in the C part of the image. If it's placed beyond point C, what will happen is that the image will be formed between C and F. The image will be real, inverted, but it will be smaller than the object. Okay, this is C, and this is D. Now, when the image is placed in the D part of the question, when the image is placed at C being here, and the image is placed at this point, what will happen is that when the object is placed at C, the image will be at C also, and it will be real, inverted, and same size as the object, because the object and image are at the same point. Now, what if the object is being placed at, between F and C? For this one now, if the object is placed between here and here, what will happen is that the image will be formed beyond C. It will be real, inverted, and it will be larger than the object, so it will be formed anywhere beyond C. And then for the last one, F, if the object is at F, one thing is certain: the image will be placed at infinity being at this point here. Alright, now let's look at images that have been formed by convex mirrors. Whatever the position of the object in a convex mirror, it's important to note that virtual images are always erect, and that they are smaller than the object that is being formed. They are always erect, and they are smaller than the object that is being formed. Now, let's look at the application of reflection of light. We see the application of reflection of light in concave mirrors, used in torch, in shaving mirrors, in car headlamps, and in reflecting telescopes. On the other hand, convex mirrors are used as driving mirrors. The reason for this is because they have a wider field of range. They are diverging mirrors, and they have a wider view of range, and the images they give are more erect than the images of concave mirrors. Concave mirrors are converging, and they are used in torches that help to focus on an object that can be in a far distance. Alright, so this is the formula for a mirror: 1 over V plus 1 over U equal to 1 over F. V is the image distance, U is the object distance, and F is the focal length of the mirror or lens. Now, when we want to find magnification, magnification simply refers to how big the image is, the ratio of the image and the object together. In other words, the height of the image and the height of the object, their ratio together, which is bigger than which. That is what gives us the magnification of the image. Alternatively, if we don't want to use image height, we can use image distance to the ratio of object distance. Now, let's find the solution to this question on the slide here. The question here is telling us that an object is placed 30 cm from a concave mirror that has a focal length of 15 cm, and we're asked to find the magnification of the image that is being produced. Here you would notice that the object distance is 30 cm and the focal length is 15 cm, and we're asked to find the image distance itself. So we use this expression: 1 over 1 over v plus 1 over u, which is equal to 1 over f. Now, since we are looking for 1 over v, so we just have to find a way to make it this subject of the formula. 1 over f alternatively equal to 1 over v plus 1 over u. Write it this way to make for easier calculations. So we have 1 over f as our 1 over 15, which is equal to 1 over v is what we're looking for. So let's write 1 over u first, which is 1 over 30 plus 1 over v. So making both of them the subjects of the equation, we can decide to have 1 over 15. 1 over 30 crosses the equality sign, it becomes minus 1 over 30 equal to 1 over v. So at the end of the day, we just have to find the LCM of 15 and 30, which is 30. So we just have to rewrite them as equivalent fractions. So 15 divided 30 is 2, and 2 times 1 is 2. 30 divided 30 is 1, 1 times 1 is 1. 2 minus 1 is 1 over 30. So what it simply means is that this 30 here is the sum of 1 over v and 1 over u, which gives us 1 over f. So this here is our f. Now, since it's our f, we just have to find our magnification, which is object distance over image distance. Image distance over object distance. This here is the value of our 1 over v, and then v is 30. V is 30 here. So we have 30 over our u, which is 30 as well. 0 will cancel 0, 3 will cancel 3. Therefore, our magnification is equal to 1, and that's how we found the 1 here. Thank you so very much for joining us in this lesson. To refresh your memory on what we've just discussed, please take the test that will appear on your